All right, hi everybody. This is Kubernetes Workgroup Device Management for March 17th. Um, let's get going. I'll display the agenda. Um, okay, yeah, why don't we just get started? Sunny, I think I saw you're online, so I can give you the co-host so you can share your screen if you want.
Okay, sounds good. Let's share the screen. I'm going to share a tab. Yeah, can everyone see the screen?
Yeah.
Okay, cool. So we are going to demo a weight propagation interface proposal here with the DRA group. We have already presented this at the SIG-Node and SIG Storage meetings, and we also want to discuss this approach specifically with the DRA group because we have a demo with DRA. Giving you a little bit of background of the problem we are trying to solve. So weight propagation in reinforcement learning is the problem we are trying to solve. Because for the model weights, the RL workflow trying to transfer usually is in hundreds of gigabytes. And the current industry direction it is going is that it will try to use the RDMA, which is the network layer, to do data transfer instead of consuming GPU or TPUs. We want to discuss if it's possible to have a standardized way to decouple the lifecycle of this data movement in Kubernetes. And that's why we are proposing this weight propagation interface. And there are a few components we identified for this specific weight propagation problem. You will always have a source, which is the sender of the weights, usually generated by the trainer in the RL world. And then the medium is what we are trying to targeting. We want to make sure it used RDMA in GPU or ICI in TPU. And then there is also the sink. There may be multiple sinks because in the RL flow, there may be multiple samplers trying to get the new weights from the trainer. And then there is also the translator layer. For our demo, we didn't get to the translator layer yet, but it's basically when the trainer and the sampler has different format of data, you will need to some way to translate it. And then there are also a few goals we define here. You can read, it's too long. But feel free to leave comments and let us know what else you think we should try to focus on solving. And then here, we give an example of the UX of WPI. There will be a few concepts here. The first one is weight buffer. You will basically define the size of the data and the provider and some layout of your data. You can think of it as a PV object, similar to the CSI interface. We are heavily referencing the CSI interface design. And then there is also this concept of weight claim. You can see we define the source buffer and you will define some policies for propagation. And then in the end, your pod can refer to this weight claim for consumption. And for the application code, this is what you will have in your application. And because there are different technologies, and this is just the example of using Nickel. If you are doing something on GPU, this part of code will be different. We are also thinking about maybe for usability, eventually it would be better for providers to have a separate library to hide the complexity of this for the customers. And there are a few components in the architecture as well. The WPI operators is basically the control service. It will monitor the creation of wait claim and wait buffers. And then on each node, we will have a WPI driver to do a few operations. For example, when the pod requests the wait claim, the WPI driver will initiate the transfer. And there are more details that you can read, but I think it's easier if we just look at the demo with DRA. And then we have a demo here on YouTube. I'm gonna play. To confirm, can everyone hear the demo?
I can't see the demo. I think it opened at a different tab and I don't hear it either.
Oh, okay.
There we go. Now we can see it.
But
try playing.
Try playing. Okay.
Hello. Today I'm going to demo the wait propagation interface, or
Yes, we can
WPI. Currently, if you want
So you can hear?
Yes.
Okay, cool.
to transfer a 75 gigabyte model from a training node to an inference node in Kubernetes, you usually have to write it to a cloud storage, and then the new inference pod has to download it from scratch. This means your new pod sits in a initialization state for minutes. It ties up your CPU to handle the network traffic, and your expensive GPUs sit idle while they wait for data to download. The LPS solves this by treating model weights as a native Kubernetes system resources, just like requesting a CPU or persistent volumes, but mapped directly into GPU VRAM. Instead of downloading huge static files, the inference engineer can simply outline the standard Kubernetes DRE declarations. Here we see a standard custom resource declaring the need for 75 capacity buffer. Once applied, the Kubernetes scheduler understands these requirements, binds any pods requesting it to a properly equipped node, and passes the instruction down to the local kubelet. The kubelet interacts via our WPI DRE plugin, managing the memory allocation lifecycle. Let's trigger the entire workflow, from staging to fabric propagation. Our orchestration will create pods calling for DRE resources on both source and the target GPU VM. Notice how standard pod creation now trigger DRE preparation in the background. Now that the staging is complete, on both ends, the WPI background dynamically streamed the 75 gigabytes payload across the RDMA network directly using NICO. Notice the speed, over 76 gigabytes per second. We just move a 75 gigabyte model with across the network between VMs in roughly 2 seconds. To see this in action in real application, let's submit the weight claim we saw earlier. Now that the data is pinned in the target VM directly over the fabric, what does the application developer experience? They deploy a standard pod, but look at the bottom of the spec. It requests a GPU buffer natively using standard Kubernetes resource claim. Because the kubelet orchestrates the DRE staging natively prior to fully starting the container, when this inference pod actually boots up, it doesn't download anything at all. It just maps the memory pointers. The pod goes from pending to running and then ready to serve requests almost instantly. And that's the real power of WPI with DRA. It brings these ultra-fast hardware transfers right into standard Kubernetes pods. You save minutes of load time, and you remove the need for all that extra network storage. That's all I want to show. Thank you very much for your time.
Yeah, and that's the demo.
That looks pretty cool. Yeah. This is so you've got a couple of CRDs to define the source and the sink, and then sounds like you have resource claims. Where's the resource claim fit in exactly? Is it you claim that it's involved in establishing the connectivity? I'm just wondering how it all fits together. Maybe we just need to read the doc because we have a bunch of things on the agenda, but that looks pretty amazing.
Yeah, so the driver does a few things, like even the identity service, and even check if you have the right capability to do the operations. There are a few APIs we defined. It's called like node propagate wait, and then like stage wait. So if you're familiar with the CSI interface, it's quite similar to that. So a lot of things are hidden in the driver itself. And right now we have an example of the two-sided transfer because Nickel is two-sided. I know for the new industry standard, like Nexo is one-sided, but I think that's like the current framework, like the current design we have should also fit into that.
Awesome. Any questions from anybody, or what are the next steps? And is there something you think you need from upstream, or do you think we have everything you need in the APIs today?
So like we just want to open the discussion to the community and gather feedback. This is the first step. We also engage the VLM and LMD folks because they have actually a link to RL North Star in one of my comments at the very top. Like they break it up into a few components for their RL flow, and then we see that they have this weight sync coordinator and Nickel Nixo weight data plane. So we want to see if it's reasonable for them as well that we break it away to a component to simplify the UX.
Awesome. Okay. Well, thank you. One thing we are doing is trying to gather like a list of use cases and drivers for discoverability and things. So I'll put it in the agenda. There's a file you can just add links to for your technology. And I mean, I don't know how much it helps, but it's at least gives us one place for people to go to discover these things.
Okay, sounds good. Can you send me the link?
Yes. Yeah, I will.
Okay, thank you.
Thanks, Sunny. All right. All right. Well, if there's no questions on that, I think Gaurav's next with a couple of items on the agenda.
Hey, can someone share their screen, or would they prefer that I share instead? Anything works for me.
I made you co-host, so go for it.
All right, awesome. Let me give this a try. Is my screen visible?
Yes.
Awesome, thank you. So I wanted to bring up a potential lifecycle issue that I observed with DRA drivers that are implemented as an NRI plugin as well. And I want to highlight the problem first of all, and then try to figure out, obviously not the full solution right now, but see if we are okay with figuring out a solution first of all in this community, within the DRA community itself. So to illustrate the problem, I have created this diagram, which I don't know if you all can see.
Yes, we can see it.
Okay, awesome. So again, for context, I'm using DRAnet as an example of something that I am closely familiar with, but the problem should happen for any DRA drivers which are also an NRI plugin at the same time. So basically, they make use of NRI to handle the device injection. So the phase 0 is, so first of all, setting the context, this is all standard stuff. Steps 1 and step 2 are basically the DRA driver registering with the kubelet and container D to say, hey, I'm the driver, make sure that you actually forward relevant API calls to me. And when I say API calls, I mean like whenever a user workload is created, which is requesting DRA resources, kubelet as a standard mechanism will make the node prepare resources call to the DRAnet driver through the DRAnet interface. And in this case, it succeeds. Now things start going south if after this node prepare resources succeeds, the DRAnet daemon or the DRA driver crashes. So in this case, what will happen is both the registration with the kubelet for the DRA interface and the container D will be stopped. Container D also has some kind of a health checking mechanism where it recognizes, okay, the NRI driver is no longer active, so it will deregister it automatically. So continuing this life cycle of the same pod getting created, which we just prepared the resources for in step 3 over here. The expectation is that the kubelet makes a run pod sandbox call to container D, step number 7. And the ideal behavior or the right thing would have been that container D makes a run pod sandbox hook execution as the NRI plugin to the DRA driver or the NRI plugin part of the DRA driver. But in this case, sadly, what has happened is because the NRI plugin is no longer active during this time, so container D opens in a fail open mechanism and it actually completely skips making this call. It still continues the creation of the pod and the containers. And what that means is that the pod is now missing anything which would have been executed as part of run pod sandbox. So basically, any devices or any modifications that run pod sandbox or create container would have done, those are completely missing. Now, the first thing that comes to our mind would obviously be that NRI and the NRI plugins should not be fail open. There should be some mechanism for us to say that, hey, ensure this NRI plugin actually does get executed. And this brings me to this specific thing which NRI plugins now support, which is that within the pod spec, you can provide this particular annotation which says, make sure when this pod is getting created that this specific NRI plugin actually gets executed. Now, where I want to, the idea that I want to throw out is that I think it's possible that we don't make the user explicitly specify this annotation and we have something which is more native because the user is already requesting DRA resources over here. So that in some way should be sufficient for this whole mechanism to make sure that that specific NRI plugin is always executed. And if it fails to get executed, then the pod creation should not succeed until the NRI plugin is back up. Now, there could be several possible solutions to this, and I'm not trying to propose a complete solution right now, but just trying to throw an idea out that what I'm thinking when I'm thinking about a closer integration between DRA and NRI is that, for example, when we are making the node prepare resources call, we modify the response to somehow include that, hey, make sure that for this specific pod, you trigger the NRI plugin. So this is a new response that we can actually provide back to the kubelet, which makes sure that when the kubelet is sending the run pod sandbox, create container calls to container D, it includes this necessary information that make sure the NRI plugin does get executed and everything works well. At this point, I'll stop and see, first of all, if we think we want a closer solution or a more native solution between DRA and NRI, if people have somehow run into this issue, obviously, or if people have some other thoughts regarding this.
I have a question. Can you go back to the previous diagram?
Sure, this one.
Yeah, so when you say DRANet crashes, that's just NRI didn't cause it to crash, right? You're just saying that DRANet process crashed for some reason, which
Yes,
triggers
yes.
the deregistration. Okay. And
Yes,
then in
and I'm
phase
not just saying
three,
it's so it could be a crash in itself, which is unexpected,
Mm.
or it could also be something like that the driver is updating to a newer version. So basically any kind of pod lifecycle event. So the
Yeah.
pod is getting deleted and recreated.
got it. And then in phase three, is the process back up at this point? That's the piece I
No,
didn't
that's
kind
the
of
thing.
see.
Like
It's
while
not,
run
it's not,
sandbox is executing, the process is not back up. Sorry, there's no way to remove this blue box over here. But after this red box, the process is not up during step 7 and 8.
So what you expect is
Mhm.
for this to fail, basically, but it's not failing.
Yes, right. So we expect
right.
this to
Sorry,
fail.
sorry,
but it
let
actually
me
proceeds.
let me ask one more question there. So whatever you were doing with the DRA side of things, I guess that succeeded before the crash?
Yes. So
Okay.
the only thing
Maybe
on
I
the
missed
DRA
that.
side is the
Okay.
node prepare
Got
resources
it.
call.
Node prepare resources succeeded, but now it hasn't done the NRI side of things.
Yes.
And okay, got it. Yep. And so yeah, pod goes down for some reason, or the DRA driver goes down for some reason, and now there's nothing blocking the sandbox creation from continuing because the prepare resources call succeeded. But
Exactly.
because that
Exactly.
pod's not up, it just doesn't do any of the NRI stuff.
Right. It
Exactly.
deregistered when really it should have not.
So,
right.
yes, it's not that. So
Well, it had to deregister because the pod went away, but somehow we needed some way of blocking the pod
We-
sandbox from succeeding because we knew that this is supposed to be doing something across NRI.
Right. We needed to know at the initial state that this was something, and this is exactly I think what Gaurav was saying. Like at the initial state, we needed to know the full process that needed to be completed. Like and it changed in the middle of it, and we don't have that state recorded anywhere. That's the full process.
Yeah, yeah. And with DRA, that state is encoded in the fact that node prepare resources must succeed. So if the pod went down at any point in this before node prepare resources succeeded, pod create sandbox would never happen because it's blocked on that point. But there's nothing like that that exists for NRI because NRI is an optional thing that you can subscribe to. There's nothing in the pod spec itself that says NRI has to be invoked at all. And I think that's what you're getting at with this annotation is that as a way to say in the pod spec, make sure NRI is invoked for me.
yes.
At least in the current way that it's designed. And your question, I guess, now is, can we do something better than forcing a user to put an annotation on their pod? Yeah.
Exactly. Yeah. Yes.
Mm-hmm.
So I'll say I think your proposal looks reasonable. I think it's also worth exploring. Like this is a common pattern, right? Of we're seeing with DRANet and others like of DRA drivers that also serve as NRI plugins. And is there a tighter integration or something, or even earlier? I don't know that there is. This seems like a pretty good, reasonable solution right now because if it fails, now you've closed the gap. Because if it fails before node prepare resources or during, then it fails, and then I guess what I don't understand is that you get the response returned. There's still a slight gap because somebody then has to record that equivalent of the annotation, that mandatory thing, in some sort of state that's gonna, or is it just in memory and the issue is that I guess it's just in memory at that point, and so because if the whole thing failed, we'd fail anyway. So it's not that we lost that state. So maybe there is no gap. So I mean, that seems like
where in the diagram? Where in the diagram are you talking
I was
about?
worried if there was the only failure we have here is the DRA plugin, not the kubelet. So the kubelet's going to still have this, even when the DRA driver fails, the kubelet's still going to have, after completion of node prepare resources, the state that
it has its answer. Yeah.
It's not like that had to be written to disk or something because there was some other failure. We're not worried about that case. We're worried about just the driver failure. So I think we're safe. There's no gap.
So I'm sure I think there will be some edge cases which pop up as we investigate this further, but at least it seems like from our discussion that this is something that we recognize as something where we need a closer integration and potentially worth looking into, right? Am I understanding that correctly, Kevin and John?
In my opinion, I think it's worth looking at this pattern of DRA drivers that are also NRI plugins and seeing what is the scope of things that would make this pattern easier and more effective. I think this might be the first, this small change looks like a pretty small change, closes this gap, which at scale, I'm sure you hit. I assume this came from actual
Right.
experience. So like that seems like, unless we come up with a better way to do it, this seems like a no-brainer in my opinion, but I think it also is worth looking at this pattern more in general. That's all I'm saying.
Yeah, I think I missed what the actual proposal is, just to not force a user to put the annotation on there.
Yes, basically, I want a solution where we don't we're not forcing the user to put this annotation because the user is already using DRA and they're already specifying their intent that, hey, they want these devices to exist in the pod. So the rest should somehow be automatic.
Yeah. And what was the proposal to do that?
The proposal was that node prepare resources return a list of the NRI hooks that must execute. And then passes that through to containerd, and that's enough for containerd to go, oh, that must execute, but that thing's not registered. I'm going to fail. Yeah. So it leaves it in the driver's hands to make the decision of which things must execute. And it's on a per prepare basis, which is kind of interesting from a it
feels a little weird to be tying the node prepare resources call to NRI. To even be aware that NRI is a thing. So because it's not even a Kubernetes thing, it's a containerd or a CRI-O thing. But yeah, go ahead.
So yeah, I mean, the idea was that obviously if you don't need NRI, or the relevant fields or whatever we add won't be set, but only when the same driver is also implementing NRI, yes, somehow we would need to make kubelet aware of this thing called NRI as well, in addition to kubelet already being aware of the DRA driver.
Yeah, no, I get the intent, but the API for it feels awkward to me because Kubernetes isn't even aware of this interface beyond us just suddenly introducing it in this response from a node prepare resources call. Yeah.
Gotcha. Feedback taken. I fully recognize that. Yeah. I don't have a better solution right now, and this is obviously not something that I was hoping would be like the final solution that we come to, but just one idea among several.
I think it's worth iterating on. Go ahead.
Yeah, I was looking on the same one from the DRA SRLV point of view, and my idea was to try and contact CRI-O and containerd people and going like on a different way, on a way where when the drivers start, we put a file to say that we need to be called by them. And if the socket is disconnected, then we failed. And if we delete the daemon for some reason completely, because we want to uninstall our application or something like that, so we remove the file. That was my initial idea. Again, you can have gaps what if the files remain on the host and things like that. But at least from my point of view, and I agree here with Kevin, I think that's something that the DRA drivers that need also NRI interface should work with NRI. It's not something that should be on the side of the DRA interface. It should be separated.
Sebastian and Kevin, is there something that can come through CDI? Because CDI is a Kubernetes, right? We do understand CDI. Is there a way we can pass the same data through CDI?
That also can be one of the options. In general, for the NRI interface right now, I would say we have two special issues here. One is this one, and another one is that there's a timeout, how much time NRI, like CRI-O containerd waits for the NRI hook to come back. And if it takes more time, it doesn't fail. It just continue with the pod start, pod sandbox start. And at least from my case, when I was testing this one with the default 2 second, if I try to put like 100 virtual functions inside the pod, it's funny, like the pod start, and if you run IPA, you start seeing more and more VF coming up after the pod is already running, because it takes more than 2 seconds that the allocation. The easy way is extend the timeout, but then you ask yourself how much to extend the timeout, another problem. So that's the two problems that right now I have with the NRI interface, that it's not like the DRA interface, that if node prepare failed or we doesn't return anything, so it will not continue. It will not just skip more or less and do other stuff. That's for NRI today.
Right. But so NRI and, so yeah, that makes sense. Like, it seems like that fail open behavior is not ideal in a lot of cases. But that definitely seems like, something Containerd and CRI-O need to sort of make available. The question is it, it's not a configuration option. Is it a configuration option on a per hook basis, or is it a work runtime choice, right? Like a runtime choice based on the particular resource claim and therefore the node prepare resources. If it's a runtime choice, then we probably need to find a way for node prepare resources to make that decision and pass it through somehow, CDI or otherwise. If it's just, my hook always needs to behave this way, then it's probably just a feature on the Containerd, the registration of the hook.
Mm-hmm. That's at least what I was hoping, like that everything can be that part that we are missing for DRA-Net and other network related that use both DRA interface and NRI interface, is that everything will be on the NRI interface. So we don't touch at all the DRA interface, and the changes needed to support these two cases needs to go specific on NRI. And I would say the reason they put it like open on fail is because you don't want to have like a chicken and egg problem, that your your NRI plugin that it's a daemon set gets restarted, but the socket is not there, so it's not able to start because NRI reject the hook. So that's why they put it right now in this way. So you have it on like allow on fail for the NRI interfaces. So yeah.
Yes.
I wonder if you. Yeah.
So adding on top of, so an argument that can be made to make this an runtime decision instead of like a static configuration decision that I had in my mind was that you don't want all the pods to remain blocking for DRA-Net. You only want those specific pods to remain blocking for DRA-Net, which have explicitly requested maybe some relevant DRA resources. On the NRI side, there is nothing which currently exists which says only these pods are of interest. It treats all of them equally. So the only part which currently makes a difference over here is that the DRA part, which is some pods may request DRA resources, some may not request DRA resources, and we only want pod lifecycle events to remain blocking for the ones which requested DRA resources,
right?
Which made me think at least that perhaps node prepare resources is the right entry point to make sure this only happens on the exact pod which we want to remain blocking and not all the pods itself. So I guess in the interest of time, I think we only have like 20 minutes left. There's a couple of hands up, and maybe we can switch to a different topic.
Okay, well, the point is we should explore more this integration and make sure this pattern works better. Yeah, I mean, whatever.
Will you be at KubeCon? We can talk about it maybe on Sunday at the Maintainer Summit.
Sadly, I will not be there, but yeah, I think Antonio will be there, so maybe I'll discuss with him, and then you guys can have some discussion.
Good, sounds good.
Praveen?
Yeah, hey, thanks Gaurav for bringing this up. I think like we could run into the same issue with the CPU DRA driver as well. So I was wondering, like, until we have like a tighter integration, could a stopgap solution be that, like, so the NRI driver also has this synchronize hook where when it is coming up, it'll pass the list of like all of the pod sandbox and the containers. So at that point, do you think like we could check the current state, and if that does not match like what we expect, could we kind of re-trigger what the NRI hook would have done had it been through like the stat container or like the rest of the other hooks? So do you think that's the
So
yeah.
got it. Thanks, Praveen. I totally feel what you're saying, but I think the problem at this point would be that the pod and the containers have all already started without the device itself. So the best that you could hope for is to somehow delete the container and restart it, which is like one of the worst things that I think you could do, because it's already started at this point. So I think by the time the NRI plugin restarts, I think it's already too late if the containers and pods have already been created. So
Okay.
we really need to make sure that the pods and containers don't get created while that thing is down.
Okay. Yeah, maybe it's not like a very generic solution, maybe very specific to CPU driver, where
I see.
you could come back and like set the CPU mask. Like, I mean, there would be some delay, but it's kind of better than like never setting it. So yeah,
You can reconcile it, but
yeah.
they can't with the networking one. Yeah.
Yeah.
Okay. Well, yeah. Why don't we go review another topic? So why don't we move on to it?
Yeah, I think this one was mostly short. I wanted to bring up the DRA and pod preemption support, which I just recently found out that DRA does not support pod priorities and preemption right now. Just trying to raise this and see if we have interest on getting something regarding this in Kubernetes 137 maybe. Do we know if like any other...
You just said you're interested, so yes, we have interest in it. I think when you raised it, other people were like, "Oh yeah, we need that." So let's let's put it into the planning. And I'm wondering if it's something that could be like arguably straight to beta, which would be really nice. So let's
Okay.
I don't know. Like that's always that's always a little bit fuzzy of a question mark, but I don't know that there's any new API associated with it. I'm not sure. So like, yeah, I'd say yes, there's interest.
Got it. Yeah, that's it from me. Thank you.
Okay, thank you. Okay, Francesco.
Hey, hello. So a few weeks, I think ago, Sebastian presented the cap about the shared containers. Sorry, the shared counters. And turns out this is also relevant, I believe, for the CPU driver. And this is because if we want eventually to support the PCI root attribute, which I think we want, by the way, then we run into a scenario on which we have different PCI roots attached to the same NUMA node and to the same CPU set. So this maps quite nicely to the concept of shared containers that Sebastian pitched. Now, I'm bringing this up to further reinforce that this announcement is nice, but I am also kind of hoping that someone in this group has an idea. But I don't know. Yeah, you can use it, but you can also do it without. So I really, in this case, we have basically a pool of resources that you can access through few entry points. So you have this set of memory controllers in this set of cores, and you have more than one PCI root, tree root attached to them. So this, I really believe that the shared containers is the cleanest solution. But my question is, anyone has other experience that we can map using the tools and the DRI primitives we already have, or?
So there's a alpha feature going into 136 that lets us model the multiple routes, right? Because allows an attribute to be a list. So for the CPUs, the adjacent PCIe routes you'd have a list of them instead of a single one. So that allows us during the scheduling time to use the match attributes with CPU, NIC, and GPU. And even if the GPU and the NIC publish a single route and the CPU publishes multiple routes, we can make sure that the ones you get all match pairwise. I don't know if that is sufficient for what you're asking for, because I don't fully understand what you're asking for. There's no consumption involved in that, right? That's about like in what I just described. That's just matching. And so there's no like share, there's no shared resource that is like, we're using this much of the PCIe bus's bandwidth. We're not doing that kind of calculation at all. I don't know if that's even useful or not, but I don't know what you're looking for exactly. But just as an FYI, that feature is, is there. I don't know if it meets your needs or not.
I can try to elaborate a bit better since we have a few minutes left. So basically, thing is, the CPU DRA driver can expose, the partitionable resource of CPU. Like, okay, I have so many NUMA nodes. Each of some NUMA nodes, they have so many CPUs, and so far so good. It maps to the model we already have, but we want to expose the device grouped as PCI root, because this is basically the best recommendation from hardware folks, and this is also the shared attribute. So we start enumerating the PCI root devices, and the Linux kernel tells us, okay, those CPUs, they are local to this PCI root, because each device has the local CPUs exposed. So far so good. You have so many roots, and we key the groups by the PCI root attribute provided by the library function. So we have instead of saying two NUMA nodes, we have in this case, in this very example from real hardware, we have 6 groups, because each NUMA node has actually 3 PCI root, because this is just how the silicon is made, So, but this is a random example. We have 6, they could be 4, they could be whatever. The point in case is that we want to use the PCI root as grouping mechanism exactly because this is more precise than the NUMA node. This is what, for example, Sasha was preaching for a long time. And so we have those groups that actually share resources, because you have, let's say, for the sake of the example, 3 roots connected to the same set of CPUs. In the silicon, you have, in this case, 100 and few many CPUs on the same silicon, 1 memory controller, so 1 NUMA node, and 3 PCI roots. So you have the actual silicon resource pool is 100 CPUs, but you can see them from 3 different, you can reach them from 3 different PCI buses. Right. So if my super fast GPU is in this, say, PCI bus 0, and I have the CPUs 0 to the 100, so I want 32, I'm happy, but then those 32 CPUs needs to be decremented by the pools, the other 2, PCI root pools, which access the same pool, because if you consume 32 CPUs from the PCI root A, B and C, which share the same silicon, they don't have 32 free anymore. So you have a shared resource pool, which you cannot address directly, but because you address them from the PCI root entry point. So this is the example which I'm kind of trying to explain.
Okay. So if okay. So how much time do we have?
No, we don't need to figure this out.
Yeah, let's take a look at this other thing and see. So I can see what you're saying, that the way you're kind of modeling it is like, okay, you've consumed all the CPUs out of that bucket, which that bucket's associated with that PCIe root. Another way, though, I'm not sure if we need to do it that way if we have this list attribute, because then the CPUs would be consumed, and so they would no longer be available as a choice for things that, to find that overlap. So I don't know, like, take a look at it and we'll see if it satisfies your need or not, and if not, then we'll look at what we have to do to fully satisfy it.
Yeah, makes sense. Thank you.
Yeah, awesome. Thank you. Okay, wow, we got through everything there. Anything else folks want to discuss? We have 10 minutes left. Okay, well, if not, then let's take 10 extra minutes to review some PRs, and we'll see you. We'll see some of you next week in Amsterdam, and otherwise see you all in a couple of weeks on this call. Thank you.